Hello everyone, here we'll be discussing double integrals over general regions. In the last video we saw double integrals over rectangles, which are very particular types of regions. Now something you can do to relate these ideas is you can actually take the double integral over a general region D. So imagine it looks something like this, kind of weird shape D in R squared, so on the xy plane imagine. And you can actually always find some rectangle R containing D. And then all you would need to do is just define this new function, capital F of x comma y, that is either lowercase f of x comma y when the point xy is in D, so imagine here, or 0 otherwise when it's in R but not in D. So that slash notation I'm writing here just means without. So R without D means it's in R but not in D. And the nice thing about this, of course, is because double integral, remember, means volume under the surface above this region. So everything in this, everything in this non-shaded region will contribute a volume of 0. So I hope that makes sense. So this is a nice way to relate those. But to be quite honest, in this section we won't really be discussing this idea. It just kind of relates things to the last video, so that's all I wanted to say there. What we'll actually be discussing though is the following. So these two types of regions. And in fact, we'll be taking a look at integrals over regions that are not of this type as well, possibly with examples after this. But for right now, let's take a look at these two types, and then we'll do examples of these types, and then we'll worry about everything else after the fact. So let's see. So we have type 1, where our region D are the points x comma y, where x are in between two constants a and b, but the y values are in between two functions of x. Type 2 is the opposite way around, where our points x, y in our region have y values that are between two constants, but the x values are between two functions of y now. So the image we get are the following. So for type 1, imagine we have the xy plane here. Type 1 will look something like this. So we have some function and some other function. So let's say this function that's above, so imagine these are the values a and b for x, and here let's say that this is g1 and this is g2. So notice this makes sense because if you pick any point in this shaded region, its x values are going to be between a and b, and its y values will be in between g1 and g2. Notice g1's on top in the shaded region. It's below after because I've kind of made it look like they intersect here, which is possible. And should have seen some idea kind of like this before when finding an area between curves possibly. But we'll be discussing this again with some examples, so we'll kind of see what's happening. For type 2 though, it's a little different. It's actually the same idea, but just kind of reversed as far as the x and y values go. So here, the y values will be constant c and d, something like that. And now we'll have these kind of sideways curves, let's say h1 and h2. And in fact, you know what, I realize now that g2 is above g1, so really my labeling was off. g2 should be greater than g1, but it really doesn't matter. I mean, it kind of matters, but again, we'll see with some examples actually what's going on. But you always want to do top minus bottom is really what this is saying. Well, not minus, but you want your top one to be larger than your bottom one. That's clearly going to be the case here. But now as far as the setup goes, I think that's really the main thing we should be discussing. So with these types in mind, the following results. We get the following result. Our double integral over the region D becomes the double integral of f of x comma y. And again, the order matters, if you remember Fabini's theorem. So it's either dx or dy first. And in this case, we actually want to do dx last. And I'll explain why. But for right now, let's just kind of keep that in mind. We want to do dy first and dx last. So with that being said, then the limits for dx must be a and b, which are constants, notice. And the limits for dy, for y, would be g1 of x and g2 of x. Now, why this is the case is because if you recall examples we did from the last video, when you take the integral with respect to y is kind of gone because you're going to plug in your y's to be these limits. So you'll still have x involved. And in fact, here, since our limits will involve x, You'll have more x's involved, really, because you're plugging in x values into y values in this case, which we'll see some examples of in a moment. Then, once you have your expression in x, then after applying the first integral, you can take the integral of that resulting expression with respect to x, then plug in these constants, and you'll actually get a numerical value. That's the whole purpose of this, is to find one value, which again represents the volume under the surface of f of x comma y above this region D. So very similarly here, we actually get quite a similar setup. In fact, it's really the same setup if you think about it. But here we're going to do dx first and dy second. And again, the reasoning there is because we want our constant limits to be the kind of final limits. And since our constant limits are with y, we want to go from c to d last. So we get an actual value. Otherwise, if you plug in variables last, then your expression will involve variables and it won't be a numerical value. It will be an expression in y in this case. Or I guess x if your limits involve x. And our first limits of x will now be these, because x is going to be in between these functions, h1 of x and h2 of x respectively. Perfect. So these are pretty, I think, good things to keep in mind. But again, the rule of thumb is that you want your constant limits to be on your outer integral, and you can possibly have variable limits here, but they shouldn't be the same as your variable of integration. So for example here, since we're doing dy first, it would make no sense to plug in y again, because you want to get rid of y. So you integrate with respect to y, then plug in these values, which will be involved with the x only, so that our expression now will be in x, and then we can integrate that with respect to x. Again, it's kind of hard to see without looking at some specific examples. So with that being said, let's take a look at some examples now. All right, so for this example, we want to evaluate this double integral over the region D, where D is the region bounded by these parabolas, y equals 2x squared and y equals 1 plus x squared. Now, the best thing really is to graph your region on the xy plane. So that's what I'm going to do. There kind of is a way to do this without graphing, which I'll try to describe in a little bit, but for right now, let's see if we can graph this. So I know y equals x squared is just a parabola centered at the origin 0, 0, and y equals 2x squared is that same parabola, but only stretched out in the y direction by a factor of 2. So I'm going to draw something similar to what I know y equals x squared to be, but a little skinnier. And this is y is equal to 2x squared. Y equals 1 plus x squared is, well, again, it's the graph of the parabola y equals x squared, but the plus 1 means it's all shifted up vertically 1 unit. So that'll actually be shifted up 1 unit, and it'll be less wide, so that they actually intersect. So this guy is going to be y is equal to 1 plus x squared. So this region here is the region we're looking for. This is the region that we're integrating over, basically. So now, notice here, we have these two functions that are in terms of x. So that tells me really this is a type 1 region. So keep that in mind. The fact that these are functions in terms of x, that implies that this is type 1. But remember that for type 1, we want our domain to be of the form, the set of x comma y points, where x is in between certain values, and y are in between certain functions. So here y will be in between, well, 2x squared and 1 plus x squared, but still the order is kind of fuzzy. Now once we graphed it, it's kind of easy to see which one's on top. Here 1 plus x squared is actually on top for our region. So really it's going to go from 2x squared to 1 plus x squared. If you didn't graph it, it's kind of hard to tell this, but I'll show you a way of finding this out without graphing it in a moment. Now as far as the x values go, it looks like one's negative and one's positive, and it looks like they're kind of the same because it's symmetric about the y-axis. But that's just the nature of these parabolas in this case. And it looks like they may be 1 and negative 1, and we can check that. When you plug in 1 here, you get, well, notice x squared, when x is 1, is just 1 times 2 is 2. Here, 1 plus 1 squared is also 2. So 1 works. Negative 1 also works because negative 1 squared is positive 1, so you get 2 for the top parabola, or I guess bottom parabola, and 2 also for the top parabola. Yeah, good. So x values are going in between negative 1 and 1. And you may ask, well, how the heck do you do that? without graphing. Here's how. You take a look at your functions, either they're both in x or both in y, but in this case they're both in x, and you set them equal to each other. Then you just solve. So notice here I can just subtract x squared to the other side, and what I end up getting is x squared is equal to 1, and we get x is equal to plus or minus 1 because square root of 1 is positive or negative 1. So there are x values, negative 1 and 1, obviously in the correct order. But then how do we get this situated? Well, all you really need to do is plug values in between and see which one's on top. So notice 0 is a good test value. So when you plug in 0, here you get 0 for 2x squared. So 2x squared would be equal to 0 when x is 0. And 1 plus x squared will be equal to 1 when x is 0. What that tells me is that 1 plus x squared is on top and 2x squared is on the bottom because it's a smaller value. And clearly when x is equal to 0, the y value for 1 plus x squared is 1, and the y value for 2x squared is 0. Which that part really doesn't matter. The whole point is you pick some number in between the x values you found. So this is a way to get the inequality situated, or the order situated. Okay, now for the fun part, the actual integration. So we know this is going to be a double integral of our function, which is x plus 2y, and we know we need to do either dx first and dy second, or the other way around. Now the way, again, we want to do this is our constants need to be last. So these are function limits, these are constant limits. So negative 1 to 1 needs to be last, and those are x limits, so we need to do dx last. So that means dy will be done first, and those limits, of course, in order are 2x and 1 plus x squared. So everything I've done up to this point is actually really, really, really important to get this setup correct. So I know it was a lot, and we spent a little bit of time doing that, but it'll make this part clear and hopefully a lot easier. So now remember, this is an iterated integral, so we'll work from the inside out. The antiderivative with respect to y of x is xy, because x is a constant. Antiderivative of 2y with respect to y is this, well, it's y to the second over 2, but then times 2, the 2's cancel. So we get y squared. And if you don't believe me, you can always just take the derivative of y squared, and it's 2y, so it checks out. Now evaluating these y's in between 2x and 1 plus x squared, which is something really we haven't quite done yet at this point, will give us the following. So it's going to be x times, remember we're replacing y with these values. So replace y with 1 plus x squared. It's going to look a little gross, but I guess it's okay. So that's the first evaluation. Minus plugging 2x squared. Yeah, that should have been 2x squared. Forgot the square. I'm sorry. We already wrote that. So that's plugging in 1 plus x squared, and now we're going to let the y's be 2x squared. So minus x times y, but remember y is replaced with 2x squared, plus, let me erase this, I hope that's okay, y squared, but again y is 2x squared. So it's a little disorientating at first, but yeah, we're plugging these values in for y. So they're not really values, they're expressions, and we're going to get some crazy expression in terms of x. Then we're going to antiderive with respect to x, and then evaluate between these limits. Yikes. So it sounds like a lot, but we're almost there. Just bear with me. The only thing I want to do here, though, is I want to simplify this as much as I can. I can distribute this, and we'll get x plus x to the third. This actually expands out as 1 plus 2 times their product is going to be 2x squared. The last one squared is going to be x to the fourth. So remember, squaring a binomial is just squaring each part of it. So 1 squared and x squared squared, and the middle term is 2 times the product of those two. And then minus this. I know this guy is going to be 2x cubed. I know this guy is going to be 2 squared, which is 4, and x squared squared is x to the fourth. So the reason I'm writing like this, of course, because I'm going to distribute this negative. So that'll give me minus 2x cubed minus 4x to the fourth. And now we need the integral of this from negative 1 to 1 dx. But notice there are some like terms here. What are the like terms? There should be some like terms. Yeah, I think I only see a few, but that's okay. These two actually combine to negative x cubed, and these two combine to negative 3x to the fourth, and that's it. Okay, that's fine. The integral is actually not going to be too hard to evaluate, but it's still going to be a little, I don't know, a little weird. So x stays the same, 1 stays the same. I'm not writing this in any particular order. 2x squared stays the same. I'm just writing the ones that don't change first. And then the single underlined ones are the cubes. They combine to negative x cubed. And the double underlined ones are the x to the fourths, and those combine to negative 3 x to the fourth. And that dx. Nice. So now what are we supposed to do? Find the antiderivative of these terms and then evaluate between these limits. So yeah, it's going to be a little much to write in this space. So let me do this. I'm going to erase this, lift this up, and continue. So we probably could have done it in the space we had, but I just wanted to obviously leave ourselves with more space just to play it safe. So antiderivative of each of these with respect to x is just going to be 1/2 x squared for the first guy, x for the second one. We have 2 over 3 x cubed. Remember, add 1 to the powers, divide by the new power. So minus 1/4 x to the fourth, minus 3 over 5 x to the fifth. Good. So that should be okay. And now we're going to look at this and evaluate it between the limits negative 1 and 1. Now when you plug in 1, these are just powers of 1, which are just 1 themselves. So really we just get the coefficients added. So that's going to be 1/2 plus 1 plus 2/3 minus 1/4 minus 3/5. It's a little bit to do this by hand, but I'll try my best. And then minus, when you plug in negative 1, so negative 1 to an even power is positive 1, but negative 1 to an odd power is negative 1. So this is going to be positive 1/2, that's going to be negative 1. This is going to be negative 1 times 2/3 is negative 2/3. This is going to be negative 1 to the fourth, that's positive 1, times this is going to be negative 1/4. And then negative 1 to the fifth is negative 1, times negative 3/5 is positive 3/5. Good grief. So let's distribute the negative here into each of these terms. There's 5 terms, geez. So we get 1/2 plus 1 plus 2/3 minus 1/4 minus 3/5 minus 1/2, so these guys cancel, plus 1, so these will actually combine, plus 2/3, so these combine, plus 1/4, so these cancel, and then minus 3/5, so these combine. Nice. So I know 1 plus 1 is 2. 2/3 plus 2/3 is 4/3. And 3/5 plus 3/5 is negative, is going to be 6/5. So if you write these as all over 15, because 5 times 3 is 15 for our common denominator, I know 2 is 30 divided by 15. If you multiply this top and bottom by 5, you end up getting 20 over 15. If you multiply this top and bottom by 3, you get 18 over 15. Perfect. 20 minus 18 is 2, plus 30 is 32. And that actually cannot be reduced, so that is our answer. Wow, what a really nice problem. Hope you enjoyed that. This is not the end of the video though, so we're going to do a few more examples, maybe as crazy as this one, which to be honest, this one actually wasn't that crazy. Just the setup is something to get used to. So let's see if we can look at something maybe a little more complicated, but hopefully at this rate, we can handle the setup a little more quickly. So let's take a look at that right now. Okay, so for this next example, we want to take a look at this double integral where D is the region bounded between these two curves, or I guess you can say, I guess they're curves on the xy plane. And here, this is a line, this is a parabola. Now, I don't want to do this by graphing. I kind of want to show the graph a little bit later, but right now let's try to see this non-graphically as far as what the regions are. So remember that D is the point x comma y, where either x is in between constants or y is in between constants. Now it's not obvious here which one's which, if this is type 1 or type 2. Maybe it's neither, who knows? There are situations, again, where we have a region that is neither of those types that we discussed. But in this case, it's actually type 2. And I'll explain why I know that it's type 2 right now. It is because of the y squared. The fact that we have a y squared kind of implies that if you solve for x, you can get a function of y. And remember, y is always a function of x, just like you can let x always be a function of y. So in this case, if you were to actually solve for x, notice you just get y squared minus 6 is equal to 2x, but if you divide by 2, that'll give you x like that. Great. So there's our x, so this is our function in terms of y. But now, what about this guy? Can we solve for x in terms of y here? Of course, just add 1. So here, we end up getting that x is equal to y plus 1. So we have our two functions. We still haven't found out what the values of y are, though. We know that they are, well, the x values will be in between these two functions of y, so that's definitely a type 2 scenario. But again, there's still a little bit to discuss. So remember what I said with the last example, we can set these equal to each other. And actually, it's better, I think, in this case to split this up. I was going to split it up as 1/2 y squared minus 3 because 6 over 2 is 3. But I'll actually leave it like this. It's not going to be too bad. So we'll set these equal to each other. Y squared minus 6 over 2 is equal to y plus 2. Multiplying both sides by 2 gives us y squared minus 6 is equal to 2y plus 2 if you distribute 2 into that side. And if you move everything to one side and factor, let's see, we get y squared minus 2y. If we subtract 2, the negative 6 minus 2 is negative 8 equals 0. We can definitely factor this. The two numbers are multiplied to negative 8 and add to negative 2. I think will be 4 and 2 in some order. Yeah, that definitely works. Notice that to multiply to negative, one of them needs to be positive, but to add to negative 2, it must be negative 4 and positive 2. And if you set each of these equal to 0, because their product is 0, so either one of them is 0, we'll get y is equal to 4 or y is equal to negative 2. Fantastic. So we've actually found out that the y values need to be in between negative 2 and 4, and the x values are in between these two functions. We still haven't figured out which one's on top and which one's below, though. But remember, we can pick a test value in between these two. So for instance, y is equal to 0 is a nice test number. So if we plug in y is equal to 0, what do we get for y squared minus 6 over 2? Well, when y is 0, this just becomes negative 6 over 2, which is negative 3. And for the other one, which was y plus 1, that gives us 1. So actually the smaller value is y squared minus 6 over 2. So that means y squared minus 6 over 2 is going to be less than or equal to x is less than or equal to y plus 1. So I've kind of overlapped that arrow a little bit, so let me erase that just so we can see this a little more clearly. And I hope that's okay. So this is our domain, and this helps us find the limits and write this setup correctly. So hope it's all right with us to erase this. I'm just going to erase this part, I think, to set up our integral, and then we'll continue. So let's see. We have a double integral of this function, xy. Okay. We know that we want our constants to be last, so our constant limits are negative 2 and 4 for y, so that's going to be dy. That means we need to do dx first. The limits for x of these functions in y, so y squared minus 6 over 2 for the bottom limit, and y plus 1 for the top limit, or I guess lower and upper limit, but that's fine. Great. So now what is the antiderivative of xy with respect to x? Well, with respect to x, y is a constant. So the antiderivative of x would be 1/2 x squared. So this is going to be 1/2 yx squared. I guess you could think of it like that, because y is a constant, comes out for free. I rearrange the order, but again, the order doesn't matter in multiplication. We're going to evaluate this between the x limits y squared minus 6 over 2 and y plus 1. When you plug this in, you get 1/2 y times y plus 1 squared minus 1/2 y times y squared minus 6 over 2 squared. Yikes. This looks like quite a bit. Now remember, this is going to be this first part here. So we can replace this thing in parentheses with whatever this result expands to. I think I'm going to have to erase this to show that though. So let's see. If we expand this y plus 1 squared out, we get y squared plus 2y plus 1. If we distribute the 1/2 y, yeah, that's fine. Distribute the 1/2 y, we get 1/2 y cubed plus 1 y squared, because 2 times 1/2 is 1, and then plus 1/2 y. Okay, here, let's see, it's going to be 1/2 y if we, let's do this. So let's score top and bottom individually. Bottom squared is 4, 2 squared is 4. If we expand this in the numerator, we get the first one squared, y to the 4th, minus 2 times our product will be negative 12y squared, and the last one squared is positive 36. And the over 4 part, I'm going to, it's going to look a little crazy if I guess let's do this. 1/2 times 1/4 is 1/8. So in other words, in the denominator, they're all going to be over 8. If we distribute the negative, they'll all change signs, and if we distribute the y, all the powers go up by 1. So the result will be the following. Negative for the first term is going to be y to the 5th. It's going to be 1/8 y to the 5th. The second one will be positive after distributing the negative. It's going to be y to the 3rd, and it's going to be 12 over 8. 12 over 8 reduces by dividing by 4 to 3 over 2, I believe. Yeah, that makes sense. And then minus, after distributing the negative, 36 over 8. 36 over 4 is 9, so it's going to be 9 over 2. And we have a y because the y distributes as well. Okay, so it was a little much to see that, but there we go, we have it. And does anything combine? Kind of. I mean, we see definitely that the thirds combine and the y's combine. And look at that, they have the same common denominator, luckily, so that's going to be good. And I'm going to have to erase this to show that, but I guess we'll do this in one take, kind of. Provided all of that was correct, but, pretty confident that's the case. So we're going to get the integral from -2 to 4 of, let's see, so I'm going to write the ones that didn't change first. So it's going to be y squared minus 1/8 y to the 5th. And then for the single underlined ones, 3 over 2 plus 1 over 2 is 4 over 2, which is just 2, y to the 3rd. Minus, for the single underlined ones, 1/2 minus 9 over 2 is 1 minus 9 to -8, so it's -8 over 2, which is -4y. And then dy. Whew, nice. Great, so far it's looking actually really good. Antiderivative of these with respect to y is 1/3 y to the 3rd minus, this is going to be y to the 6th, but then we divide by the new power 6. So if you're dividing 1/8 by 6, you're multiplying 6 in the denominator. So that gives you 1 over 48 actually. If you add 1 to the power here, you get 4. 2 over 4 reduces to 1/2 y to the 4th. If you add 1 to the power here, you get 2. 4 over 2 is 2 y squared. And then we need to evaluate this whole thing in between the limits -2 and 4. So we'll indeed get a single number here. We won't get an expression of a variable, which is why, again, just reminding us, our limits have to be, or outer limits anyways, have to be constants. It's just to save some space and time, I've actually done this evaluation off screen, and plug in 4, believe it or not, you get 32, and plug in a -2, you actually get -4. So with that being said, 32 minus -4 is positive 36. Again, I just wanted to do the calculation off screen to save a little bit of time and space, but of course you can verify these values on your own. It's not too bad, it's just a lot of fraction work. So if you want to do this by hand, it takes a little bit of time, but with a calculator alongside, it shouldn't be too hard to figure out. And with that being said, let's move on to the next example then. Okay, so for this example, we kind of have this interesting situation. As it turns out, this double integral, really this is set up as an iterated integral. They don't even describe the region D in this case. They already give us the setup. But as it turns out, it's a terrible setup. It's kind of like, basically you have to work around and go backwards in some sense. The reason why this setup is pretty bad is because the first integral is dy, and the antiderivative sign of y squared with respect to y is not possible. As it turns out, this is a function that is not integrable with respect to that variable. So what that tells me is that maybe there's a way to swap these somehow, and there kind of is. But first we have to kind of realize what this domain is saying. So this region here is the set of all points x comma y, where, well, x, the last differential here is x, so the limits are in between 0 and 1 for x, and y are in between x and 1, like this. So actually we can graph this to kind of see what's going on, but notice if we want to reverse this, then basically what we want to do is find a different region. Well, it's going to be the same region, but just explained differently. So I want to explain this region by some constant y values now, hopefully, and some function x values then. So really what we can do, non-graphically I guess, is solve for x for each of these. So really this says that for the lower limit y is equal to x, and then for the upper limit y is equal to 1. So we can find out what x is for each of them. Now, here this tells us that if y is equal to x, then x is of course equal to y. So that part's fine. Here, this becomes a little harder to see what x is equal to and y is 1. For that reason, I think there really is no way of doing this without graphing. Maybe there's a way of seeing it, but anyways, I'll just graph this so we can visualize. So let's see, on the xy plane, it looks a little crooked. Let me just do that again. Sorry. Looks a little better, maybe. Yeah, looks better. So for the xy plane, we have our x values are in between 0 and 1. Let's imagine it's like this. Okay. Now our y values are going to be in between x and 1. Now y equals x is this line. It actually passes through 1, 1. So if you want to think of this as this guy here, this is y equals 1. Let's say, let me draw that dotted actually. But this is indeed the line y is equal to x, and the line y equals 1 is actually this line. So maybe we don't need it dotted actually after all. So this is y equals 1. So let's see if we can determine which triangle this is, because there's kind of these two triangles. And they may be different for all we know, or at least the integral may be different over each of the regions, so it kind of depends. But here, x is in between 0 and 1, and y is at most 1, but smallest, it's on the line. So the region is actually like this. All right, good. So this is a type 1 scenario. We want to turn this into a type 2 scenario. So we've already said that x is equal to y, but now our y values are in between 0 and 1 clearly. And it looks like our x values, the largest x can be is on the line y equals x. So x is equal to y. And the lowest it can be is actually at x equals 0. So again, that's hard to view because it's sideways. But if you imagine swapping the x and y coordinates, it becomes a little easier to look at, in my opinion. So here this is the line y equals x, or if you like, x equals y. And this is the line y equals 1. So in reality, this image now, flipped, becomes this region down here. Which is really still a positive region. I mean, you can kind of see what's going on. If you were to, again, swap these, you end up getting this exact image here. But notice the y values are in between 0 and 1 clearly, and the x values are in between, well, 0, so that's the y-axis, is x equals 0, and the largest x can be is actually on the line x equals y. So that, I know it's a little hard to figure that out, but that's what it ends up being. So this actually helps because now we can set up this double integral. We're going to reset it up basically, because the integrand of course was sine of y squared, but now instead of dy dx we're going to reverse the order of integration, dx dy, and dy will have the limits 0, 1, and x will have the limits 0 and y. Nice. Now why does this help? It helps because this is purely in terms of y, and actually you can pull that out of the integral in fact, but I'm going to do this a little differently. I'm going to just say the antiderivative of a constant is itself times x. So it's going to be the integral from 0 to 1 of sine of y times x, sine of y squared times x really, evaluated between 0 and y. And then we have our dy. Now when you plug in x to be 0, this just becomes 0, that times 0. When you plug in y, it's sine of y squared times y, which is the integral from 0 to 1 of y times sine of y squared. Which actually is just a simple u substitution. If u is equal to y squared, then du is equal to 2y dy, in which case 1/2 du is equal to y dy. And that's extremely helpful because actually, notice, y dy is here. So we can replace y dy with this 1/2 du. And since 1/2 is a constant, we can pull it out of the integral. So the 1/2 gets pulled out. The integrand now becomes sine of u, du. Notice the antiderivative of sine is negative cosine, so this becomes negative 1/2 cosine of u, evaluated between our limits. Now, since we're in u, we can change the limits, or we can back substitute into y and use the original y limits. But I'm going to change the limits actually. Notice when y is 0, u is 0 squared, which is still 0. When y is 1, u is 1 squared, which is still 1 actually. So the limits coincidentally stay the same. When you plug in 1 and 0, you just get, okay, it's kind of funny, but you end up getting this. Negative 1/2 cosine of 1 for the first evaluation minus negative 1/2 cosine of 0 for the second evaluation. Now cosine of 0 is just 1, so this is really double negative 1/2, which is positive 1/2. So we write it like this. 1/2 minus 1/2 cosine of 1. If you want to approximate this, you can. Cosine of 1 is kind of a weird number because we're taking cosine of 1 radian basically, but I'll allow you to approximate on your own afterwards. But yeah, that's all I wanted to say there. And the last thing we need to discuss for this video though are some properties of double integration over general regions. And they're going to be pretty useful in the future. So let's take a look at some of those right now. Okay, so here we're going to discuss these two properties of the double integral over the region D, general region D, of the function f of x comma y dA. But before we do that, let's recall some properties that are actually analogous to these properties we'll be discussing right now. And the first one is that the integral from a to b of f of x dx can actually be written as the integral from a to c of that function plus the integral from c to b of that function, provided that a to b is a continuous interval. Well, I guess f really is continuous over that interval, and c is some value that's in between a and b. So really what I'm saying here is that if c is some number in between a and b, then the area under the curve from a to b is the area from a to c plus the area from c to b. So if you add these two individual areas, you'll get the complete area under the curve. So that intuitively makes sense. This one is kind of funny. This is the integral from a to b dx is just b minus a. Now, of course, really the integrand here would be 1. And notice the integral of 1, or antiderivative of 1 with respect to x, is just x itself. And then evaluating x between b and a is just the difference, because plugging in x equals b and x equals a and subtracting just gives you b minus a. Now the visualization here is that if your integrand is y equals 1, then this area is going to be this distance, which is b minus a, times this distance, which is 1. So the area will actually have, well, value equal to the length of the interval b minus a, which is kind of interesting. Okay, so now how do we come up with some analogous properties to the double integral over a general region D? And here's how we do it. So we can say that the double integral of a general region D of f of x comma y dA is equal to the double integral over D1 plus the double integral over D2, where D is equal to D1 union D2. In other words, you can think of, on the xy plane, that the domain D, or I guess the region D, really, so this is D, actually is divided into two regions, D1 and D2. So basically we're splitting the region that we're integrating over into two regions that complete that region. Kind of like here, we're integrating with respect to the, well, not with respect to, we're integrating over the interval AB, and we're actually splitting this up over these two subintervals that complete that interval AB. So here we're splitting this domain into smaller pieces that combine to be the entire region D. Now this is useful when you have a situation of a domain, or I guess we keep saying domain because of D, but when you have a general region that is not type 1 or type 2, you can actually split it up into situations where they're each type 1 and type 2 individually, but you have to split it up and then thus do two integrals or possibly more, just kind of depending. So I'm actually not going to do any examples of that, but I'm just showing the property is indeed a thing, and it's analogous to this property over functions in one variable. Now the second property that's the kind of double integral version of this is kind of interesting. Here this says that the integral over d of 1 dA is just the area of d. So a of d, or a parentheses d, just means the area of d itself. And the reason why this is true becomes pretty obvious once you start to graph things. So let's imagine again that in 3 space we have this situation where we're integrating over to this general region D. So anytime I draw the xy plane like this is our floor as far as integration goes. Now, if our integrand is 1, that's going to be z equals 1 actually. So much like we had y equals 1 be in this line, z equals 1 will actually be this plane that kind of covers over like that. Now, if you project this domain up, you end up getting this kind of solid. Now, the volume of this solid, so this is the region or the surface of that, over that region. This is the surface of the, yeah, so it sounds kind of funny, but, so the plane is just flat, but then if you project to the surface, you only get like this kind of cutout of that. And the volume of this solid actually is just the base region, which is the area of the region, times the height. But since the height is 1 itself, you end up getting the area itself. So it's a little while to explain, but again, it's just because of what we know areas to be, or I guess volumes to be. So again, it's just kind of the situation where you have this domain. The area of this would be, let's say, A of D. If the height is 1, then the volume is equal to the area times 1, which just so happens to be the area. Kind of like here, the area under the curve y equals 1 so happens to be the length of the interval. So again, it's kind of like the next level of this. So again, here area is equal to the length as it turns out. Here the volume is coincidentally equal to the area as it turns out. Okay, so I hope that's okay. That's the last thing again I wanted to say for this video. Really hope we enjoyed it. It was kind of a lot really. We didn't see too many examples, but the examples we saw I think were in-depth enough. And with that being said, I'll see you in the next videos where we'll be discussing actually, well, more of this, but we'll eventually lead into triple integrals. So that's going to be really interesting when we get to that, because it's kind of, well, iterated integrals, but then we have to kind of think a little more and possibly reorder the order of integration, kind of like with the last example. So like always, hope you enjoyed this. Thank you for watching it, and I'll see you in the next video. See you then.